This video discusses the definite integral of calculus. This corresponds to section 5.2 in the OpenStax Calculus book, Volume 1. There are several learning objectives for this particular section. First, we want to state the definition of the definite integral, as you see here at the beginning. We've already talked in the previous video over the antiderivative about what an integrand is. And we've also talked about the differential and the variable of integration. We have not, however, seen yet what limits of integration are and how they relate to the integrand and the differential, the variable of integration. Then we'll talk about what is possible in order for a function to be integrable, what conditions are required. We'll talk about the relationship between the definite integral and net area as well as total area. Note that net area and total area are not the same, just as your total income and your net income are not the same. We'll use geometry and various geometric formulas such as the area of a circle, the area of a rectangle, and the area of a triangle, and the properties of definite integrals in order to evaluate them. We won't be able to learn the actual function and properties for evaluating a definite integral until the next section when we cover the fundamental theorem of calculus. The final thing we'll look at is what it means to have an average value of a function over a closed interval. Let's get started. First, we want to talk about Riemann sums and just briefly remind you what is a Riemann sum. Remember that these are named in honor of the German mathematician who discovered many of their properties. We've discovered that we can approximate the area under a curve by adding up the area of a bunch of rectangles, where the width of each box is given by the change in the x value, and the height of each box is given by the height on the function at a particular point called x sub I star. If you add up the area of the boxes, you can approximate the area between the function and the curve. This requires the function to be continuous and not negative over the interval from a to b. This is the Riemann sum. If you take the limit of the Riemann sum as the number of boxes goes to infinity, or as the width of each box, which is given by delta x, goes to 0, then you will come up with a precise formula for the area. The limit of a Riemann sum is exactly the area between the curve and the x-axis. Remember now what the definition is going to give us. In this case, this is one of the most important definitions in all of calculus. This is the definition of the definite integral, not to be confused with the definition of the indefinite integral. Remember from section 4.10 when we were discussing antiderivatives, the definition of an indefinite integral is a family of functions that are the antiderivative to the original integrand with respect to the same variable found in the differential. The definite integral is very different. It looks very similar, but it is not. If you have a function defined on a closed interval from a to b, the definite integral is given with very similar notation to the indefinite, but it has two values on the integral symbol itself, one at the lower end and one at the upper end. These are called the limits of integration. The lower limit is found at the bottom of the integral symbol, and the upper limit is found at the top of the integral symbol. These represent the area under the curve. If you look above, you will see that this expression on the right is precisely the limit of the Riemann sum. But we know that the limit of the Riemann sum gives us exactly the area under the curve, which means that in fact the definite integral is a number, not a function, not a family of functions. The definite integral is a number which represents the area under the curve between x equal a and x equal b, provided that the limit exists. If the limit exists, then we say it's integrable over that closed interval and that it is an integrable function. Let's talk about the differences now between the two. What are the differences between the definite integral and the indefinite integral? They do look similar, but they are different. Here are some of the differences between the two. A definite integral, which we are learning about now for the first time, have limits of integration on the integral symbol. These are the numbers at the bottom of the integral symbol, the lower limit of integration, and the number at the top of the integral symbol, the upper limit of integration. In this example here, the lower limit of integration is 0 and the upper limit of integration is 4. Compare that to the indefinite integral. Indefinite integrals do not have limits of integration. They are not considered over any particular closed interval. When you do a definite integral, for the answer, you get some finite real number provided that the limit exists. For an indefinite integral, when you get an answer, provided the answer exists, you get a function, a family of functions up to the constant plus c. The definite integral represents the area under the curve between the curve and the x-axis. On the other hand, the indefinite integral represents a family of antiderivative functions to the integrand. Remember that the integrand is the function that appears between the integral symbol and the differential. The variable in the differential for a definite integral is a dummy variable that disappears from the result. Remember that the result of a definite integral is a finite real number. There's no variable present. In that case, it doesn't matter whether I write the definite integral with respect to the variable x, or t, or even a star, or a heart in this case. In an indefinite integral, the differential does matter. Because we end up with a family of antiderivative functions, the variable that's used in the differential is the variable that will show up in the antiderivative family of functions. Certainly, these four families of functions are related, but the variable inside them is different. Note also that these mean that these are not the same function. It could be that x, t, and the heart have different real-world meanings. What then is required for a function to be integrable? First, if the function is continuous on a closed interval from a to b, then we can integrate the function over the closed interval. This is not, however, a necessary condition, what we call a sufficient but not necessary condition. In other words, being continuous does guarantee that the definite integral exists, but it may exist even if it's not continuous. When would that happen? In general, a function that is not continuous on the closed interval from a to b could still be integrable depending on how many discontinuities it has and what kind of discontinuities it has. Remember that we have 4 different kinds of discontinuity. Let's remind ourselves what they are. Some discontinuities are holes. A hole is a discontinuity that the integral will be able to deal with and skip across. We also have what are called displaced points. This is also something that the integral, the definite integral, can deal with. In the next case, we have what are called jumps. The definite integral can deal with jumps provided that there's only a finite number of jumps within the closed interval. If there are infinitely many jumps within the closed interval, then the function may not be integrable after all. The one kind of discontinuity that a definite integral cannot deal with at this point is the infinite asymptote. If we're looking at an asymptote and it approaches that line, the definite integral will not be able to integrate across whatever that value is. Let's suppose that that value instead of a is a c, and that a is to its left and b is to its right. When an infinite discontinuity appears inside the closed interval, we will not be doing the integration across that interval. This is something that is not actually in your textbook, but something that you should understand. If f is a continuous function on the closed interval from a to b, or if the function is bounded on closed a to b, and there are only a finite number of discontinuities on a to b, then the function is integrable. Let's talk about what this means. Let's draw a quick picture of the two situations that are mentioned here. I've drawn for you two different pictures that represent these two situations. Let's talk about them separately. Condition 1, if the function is continuous over the closed interval from a to b, then it is integrable on a to b. What that implies is that if you have a continuous function over the interval and you were connect the function with the points a0 and b0 with vertical lines x equal a and x equal b, then you should be able to shade the region directly underneath that curve between the curve and the x-axis. That must have some finite amount of area. That's what they mean when they say if the function is continuous over the closed interval, then it must be integrable over that closed interval. Now let's take a look at condition 2. In condition 2, it says the function is bounded on closed AB. By bounded, they mean that there is some constant real number, m, where m is positive, such that the function values are between m and negative m. For convenience, I've listed my function as being strictly greater than 0, which of course implies it must be larger than negative m, which must be way down here somewhere. That means that the function's y values between a and b are in fact bounded between negative m and m. Now it could be that outside of that interval, I again have some kind of infinite asymptote, or that the function goes towards infinity forever. In that case, it is not bounded when I get above b. Bounded means the y values are trapped between two positive real numbers, one above and then the negative of that number below. If that's true, and if there are a finite number of discontinuities on that closed interval from a to b, then the function is integrable. What do they mean by finite? You'll notice here I have 1, 2 jump discontinuities. That's finite. If I had an infinite number of them, then I would have difficulty. The thinking goes as follows. If I were to look only at that one single spot where the jump discontinuities occur, and I focus on one of them at a time, say this one, how much area is truly under that one single spot? Well, of course, there's 0 area under it because while it does have height, there's no width. So there's 0 area under one particular spot. If you have a finite number of these, then what you are doing in essence is you are adding 0 together a finite number of times. As long as this is finite, then you will end up with 0 again. However, if you have an infinite number of jump discontinuities, then you are adding 0 to itself forever and ever and ever, and that's an infinite number of zeros added together, which is the same as 0 times infinity, which you know to be an indeterminate value. That means the limit may or may not exist. That's why we're required to have a finite number of discontinuities on that closed interval. Again, this may or may not be required. It is sufficient, but it may not be necessary. In the next section, we'll learn to do definite integrals without considering Riemann sums or geometric formulas. However, in this section, you may have to use both a left Riemann sum, a right Riemann sum, or a midpoint Riemann sum to average or to find an approximation for the area under the curve. We will definitely be using geometric formulas for the area of rectangles, triangles, and circles in this section. This is not the normal way of computing a definite integral. However, we need the fundamental theorem of calculus to be able to get around that. We're going to start with curves that are entirely above the x-axis, but we will also look at some that extend above and below. Let's look at our first example. In example 1, we're asked to find the area under the curve f of x equal to 2x plus 4 on the closed interval between 0 and 4. I've produced a picture of the graph here using Desmos. You'll see that it does cross the y-axis at 4, has a slope of 2, and is extending only between the vertical lines x equals 0 and x equals 4. This then is asking us to find the area between the curve and the x-axis on this closed interval. That is the definite integral. We take the function 2x plus 4 to serve as the integrand. We take the closed interval values for our limits of integration. The left endpoint of the closed interval 0 becomes the lower limit of integration. The right endpoint 4 becomes the upper limit of integration. It does not matter whether we use x, a star, a heart, or a happy face, since the definite integral will give us a finite real number if that limit exists. Now, how are you supposed to do this in this section given that you don't know the fundamental theorem of calculus? Simple. Let's take a look at this picture and see how we can divide it up and use the formulas for the area of a rectangle, a triangle, or a circle in order to compute the area between that curve and the x-axis. We'll start by drawing the lines that close off our region. First, we have the line itself that you see here in red. Then we have the vertical line, which corresponds to x equals the right endpoint of the closed interval, x equals 4. Then we have the vertical line, which corresponds to x equal the left endpoint of the closed interval, x equals 0. This is, of course, just the y-axis. Now, the next point that we have when we talk about area under a curve is always implied. It's not stated, but it's implied. And that is, of course, the x-axis itself, y equals 0. Now we need to shade in the region that's completely trapped by those 4 different curves. This is going to give me this region in here. If I were to color this in, I need to know what is the area of that space right there. If you look at the space, you should be able to begin to see that there are in fact a rectangle and a triangle within that space. Let's look at that now. If I were to cut this off here where it intersects the y-axis at 0, 4, this would give me in fact a triangle here, which is in fact a right triangle, and below it a rectangle. Now let's compute the area under the curve by using the formulas for the area of the rectangle and the area of the triangle. In this particular problem, if I look at this region down here, it is 4 wide and 4 tall, which means it's actually a square. That means for the area of the square, I have 4 times 4, or 16. If I look at the triangle is also 4 wide, but it is in fact, let's see how tall. From 4 to 12 would give me a difference of 8. The formula for the area of a triangle is 1/2 the base times the height, or 1/2 the rectangle of which the triangle is half. The base is again 4, and the height is from 12 down to 4, or 12 minus 4, which is 8. That also gives us 16, which means that the area between that function and the x-axis on the closed interval 0 to 4 is 32. That's our answer. There's no variable present, it's just 32. Let's look at example 2. In this example, it says find the area under the curve of f of x equal to the square root of 4 minus x minus 1, the quantity, squared, on the closed interval from -1 to 3. I've gone ahead and graphed it for you, and you'll notice that it is in fact a half circle. Now, how would you know if I hadn't graphed it for you that it was in fact a half circle? One of the things you could do is to replace the f of x with y and write y equals the square root of 4 minus the x minus 1, the quantity, squared. In order to get this in a better form, you could consider squaring both sides. Now you know that the positive radical will only give you the upper part of something, but I could write y squared equals 4 minus the quantity x minus 1 quantity squared. Then I could put the x minus 1, the binomial factor that's being squared, onto the left side by adding it to both sides of the equation. That would move it to the left to join the y squared. If I do that, then I will get, in the next line down, that x minus 1 in parentheses squared plus y squared equals 4. This must be the equation of a circle with a center at -1 opposite, which would be 1, 0. Remember that when you do these, you take the opposite of the number in parentheses. The opposite of -1 is 1, and since y has no parentheses, the y coordinate of the center is at 0. The radius, of course, would be 2. Now that we know that it's a circle, go back to the original and notice that it is the positive radical. The positive radical is the upper part. To get the lower part of the circle, you would need a negative out in front of the radical. Now that I know that it's a circle, I need the formula for the area of a circle. The area of a circle is going to be pi r squared. I know what the radius of this circle is. I found it down here to be 2, the square root of the constant 4. However, I don't have a full circle. I have half a circle. That means the area of the semicircle, or half circle, would be half of pi r squared. Since I know that the radius is 2, I can plug the 2 into the formula, and that would give me the value 1/2 pi times 2 squared, which is 4, divided by 2, which would give me 2 pi. That would be the area underneath the curve between -1 and 3. You'll notice that I filled this in with Riemann sums. Can you see which Riemann sum it is? Notice that it is an underestimation as it increases and an overestimation as it decreases. It is the left Riemann sum, since it is the left point of each box that serves as the height of the box. Now we want to talk about signed area. What if the function does not stay entirely above the x-axis? What if part of the function goes below the x-axis? Because you go below the x-axis, that means the y value will be negative. Hence, when you multiply the y value by the width of the box, you should get a negative area. Area below the x-axis is negative, and area above the x-axis is positive. This is what we mean when we talk about net signed area. Net signed area could end up being a positive number, a negative number, or even 0. If the area of your function over the closed interval above the x-axis is larger than the area below the x-axis, then your net signed area will end up positive. On the other hand, if you have more space, more area under the x-axis than you have over the x-axis, your net signed area will be negative. What if the areas above and below the axis are actually equal? This can happen with symmetric graphs. In that case, the net signed area will actually be 0. Let's look now at example 2. In example 2, we're asked to find the area under the curve of the function 2x plus 4 on the closed interval from -5 to 2. I've again produced the graph for you using Desmos between -5 and +2. You'll see that the line is indeed 2x plus 4, crossing the y-axis at 4 with a slope of 2. We want to find the exact area under the curve. We can use triangles to help us do this. Notice that on Desmos, they've made the area above the curve blue and the area below the curve red. The area below the curve will be negative, whilst the area above the curve will be positive. It's not entirely clear which has more area, but it does look slightly as though there might be more area above. We'll have to compute it to find out. Let's split this into two different triangles and compute the area. To do that, we will need to produce again vertical lines that correspond to the left endpoint of the closed interval at -5, and another vertical line at the right endpoint of the closed interval, which is x = 2. We also need to darken actually the function, which is 2x + 4. Now we need to darken the x-axis. This is the final piece that many students forget. It is always the area between the curve and the x-axis when we talk about area under a curve. Thus, we will darken the x-axis. Now we need to find regions that are completely closed in by what we're looking at. In this case, I'm going to switch and use red for below and yellow for above. Let's shade the negative area which is below the x-axis and in this region. Notice that this region would, as I say, hold water. If you were to pour water in here, it would be blocked by getting out by the vertical line x = -5, by the x-axis y = 0, and by the function itself y = 2x + 4. No other region over here in this part is completely trapped. We do have another trapped region here. Let's shade that with yellow. This gives me this region here, which is also completely trapped, in this case by the x-axis y = 0, by the vertical line x = 2, and by the function itself y = 2x + 4. The yellow region will be positive, the red region will be negative. Now let's compute the area using the formulas for triangles. If I'm looking at the area that is above the axis, then I need to find the area of that triangle. Using the formula 1/2 base times height, I need to know when this particular function crosses the x-axis. I can go off to the side and I can compute that y = 2x + 4 will hit the x-axis when y = 0. If y = 0, then that implies that 0 = 2x + 4, which means that -4 = 2x. Dividing by 2 gives me that the x-intercept is -2. You could also read it directly off of the graph. That means that my base must be 1, 2, 3, 4 wide, which gives me 1/2 times the base of 4. Now I need the height. Where does this line cross this vertical line? Again, let's go off to the side and compute where that happens. I need to know when the x value here is 2, what the y value is on the function. If the x value is 2, then I can plug that x value into the equation to find that the intersection point here must be 2, 8. That gives me the height of this box from 0 to 8 as 8. Now that I have that, I can compute that that amount of area, of course, would give me 16. What about the other box that is below the axis? If I'm looking at that box, I know that this intersection is at -2, as I found down here. What would it be here? Well, this is on the line -5. Between -2 and -5, that triangle is 3 wide. That means I need to add on to this 1/2 times 3 times the height of that triangle. In this case, the height is a negative value because I am going down. This means I need to know when the function crosses the line x equal -5. I can compute that by going to the equation to the line and plugging in -5 in place of x. That would give me -10 plus 4, which is the y value -6. This point down here must be -5, -6. That makes the height of that particular box -6. That's where the signed area is coming from. The next thing I need to do is compute the signed area. The 1/3 and the 3 will cancel, and I get -6 for the area under the curve. That gives me 16 square units above and 6 square units below, and that gives me a net signed area of 10 square units. Let's move on to the next. In example 3, I've given you a function which involves an absolute value. It has been reflected vertically because there's a negative outside the absolute value, and shifted up 1 because there's a +1 also outside the absolute value. This gives us the graph that you see here on the right. Again, I have given you the area between the closed values x equals 0 and x equals 2. I've put them up here in blue above and red below. This gives us the area on the function between the function and the x-axis over the closed interval from 0 to 2. The definite integral then, we take the left endpoint of the closed interval as the lower limit and the right endpoint as the upper limit. If we do that, then we use the function as the integrand. Using the formulas for triangles, let's compute the area above and below. In this case, for the area above, I do have again a triangle. I can read these directly off the graph, which basically means that when x is 1, I would get 0. This point right here, where they intersect with the x-axis, must be 1, 0. Now when I compute the area above there, I take the area of the triangle, which is 1/2, the base, which is 1, and the height, which is also 1. I need to add to that the area that is below the x-axis. That would be this region here in red. It also has a base that is 2. But the height now, or rather not 2, 1, I have to pay attention to the scale. Since this is 2, then this is from 1 to 2, which represents a length of 1. The height, however, is below, which means the height is -1. Since the height is -1, what I end up with for the area, the signed area, is 1/2 minus 1/2, which gives me 0. In other words, if you look at the picture, I have exactly the same amount of area above the x-axis as I have below the x-axis. That makes the net signed area, or area under the curve, on that closed interval be 0. Now that we've talked about net signed area, let's talk about total area. Total area and net area are not the same. Your total income is the amount of money that you are paid on a yearly basis, split apart into whatever the number of payments you receive per year. If you look at that, however, and you compare it to your actual paycheck, they're definitely not the same. Before you receive your paycheck, they take out things like taxes, Social Security, and they may take out as well some other items. The amount of money on your actual check, that's your net payment. Your total payment might include the taxes, the Social Security, and anything else before it was taken out. Total area and net area are similar. Let's consider what total area might represent if we were talking about a velocity function. The velocity of an object as a function of time, if it is a constant and we were to graph it as velocity versus time, then what would the area under the curve be giving us? In other words, If this represented on the y-axis the velocity with respect to time, and our horizontal axis was time, then what would the area represent? Let's suppose that I wanted to know something about the area between x or t equals 0 and t equal 2. If I were looking at that region there, what would the area between the t-axis and the two endpoints of the closed interval under the curve represent? Let's shade in the area to see. If I shade in that area, and this time I've used the pink again, what does that actually represent? Since that's a rectangle, I can easily compute the area. I know that it is 2 wide, and that represents time, so that must be 2 hours wide. I know that the y-axis represents velocity, and I can see here that it's 60 miles per hour, a constant velocity function. So the height of my rectangle must represent 60 miles per hour. If I multiply miles per hour by hours, I should end up with, you got it, miles. This gives me 120 miles. This represents the displacement of the object from its initial position. If we're looking at that, then what it means is that over a 2-hour period at a constant velocity of 60 miles per hour, the area under the function represents how far the object has gone from its original starting place. In this case, the displacement is 120 miles. Net signed area, on the other hand, allows us to take into account the direction that the object is traveling. Is the object traveling north or is the object traveling south? The area above the axis and the area below the axis in this particular drawing are equal. The net signed area would be 0. What do you suppose that would mean in the context of a velocity versus time graph? Let's ensure that in fact these areas are 0. For the box above the axis, I have 2 hours times the constant velocity represented at the top by the horizontal bar at 60 as 60 miles per hour. That means the displacement over that particular region was 120 miles, presumably in the northerly direction, because the velocity was a positive 60, and that means I was headed north. In this lower region that is below the t-axis, what do we have? We have from 2 hours to 5 hours, which is a change of 3 hours. Over this region, our velocity is a constant negative 40 miles per hour. The negative 40 miles per hour represents that it must have been headed in the southern direction. And this would give me a displacement of negative 120 miles, which means my net signed area would be 0. What this represents is the simple fact that if I started and headed north and went for 120 miles, and then I headed south and went for 120 miles, my net displacement and net area means that if my displacement is 0, the net area represents the displacement. On the other hand, I've now been in the car for 5 hours, and I certainly don't feel like I haven't gone anywhere. I feel like I've been in the car and I've traveled for 240 miles. That is what we mean by total area. Total area would take the absolute value of any part that fell below the axis. That would tell us that the distance traveled is 240 miles, even though the displacement puts us right back where we started at 0. Total area then is the area between the curve and the x-axis, regardless of whether it's above or below. We can represent that with absolute values. This represents the total distance traveled. For example, if we start in Denver and we drive to Colorado Springs, it's a distance of 70 miles. Then if we turn around and we drive back to Denver, our displacement is 0 because we ended up back where we started in Denver. That's the net signed area. On the other hand, I definitely feel like I've traveled 140 miles. That's the total area. The definition then is the following. Supposing that you have a function for which you can compute the definite integral over a closed interval from a to b. Suppose a1 represents the area between the function and the x-axis that lies above the x-axis, and a2 represents the area between the function and the x-axis that is below the axis. Then the net signed area is a1 minus a2, assuming that both a1 and a2 are positive values. The total area, on the other hand, would be a1 plus a2. Again, net area gives us displacement, total area gives us total distance traveled. Let's look at example 4 and find both the net signed area and the total area. In these equations, we're going to have to use our knowledge about the area of triangles and semicircles in order to compute it. How are we going to proceed? First off, how can you even recognize whether or not x squared with a negative at the front plus 2x is a semicircle? Is it a semicircle? How can you determine that? Let's pull the negative x squared plus 2x to the side. We're going to need to deal with it separately. First, I don't like the leading negative, so I'm going to factor it out and rewrite it as x squared minus 2x. My next step is going to be to complete the square. If you don't remember completing the square, there's a folder on D2L to help you. Let's run through the steps briefly. In this case, I need to find what I have here, which is going to be b over a. b over a gives me, from my original b of 2 divided by my original a, which was negative 1, the negative 2 that now appears inside the parentheses. The next thing I need to do, now that the coefficient of x squared is positive 1, is take half of that value. Half of b over a would be half of the negative 2, which is negative 1. When I'm done completing the square, I will have x and a minus 1 inside the binomial being squared. In order to find out what number I need to add to force this to happen, I take the half of b over a and I square it. The half of b over a quantity squared gives me a positive 1. I'm going to add the 1 and subtract the 1 in the parentheses. We call this adding 0. Adding 0 does not change the value of the expression. It does, however, give me a different way of writing it. The first 3 terms inside the parentheses become the binomial squared. The last term, however, is not a part of it. I need to bounce out that negative 1 by multiplying it by the leading coefficient, which is also negative 1. On the outside, then, this gives me a negative 1 times the negative 1 on the inside, which lets me rewrite it as negative x minus 1 quantity squared plus 1. If you want to turn it around again, you certainly can. This is going to be the equation for a semicircle. The center here is at a different value. Let's write it in terms of y so we can see that. If I wrote y equals negative quantity x minus 1 squared plus 1, and I move the binomial squared to the left, I could write x minus 1 quantity squared. Now, one thing I've forgotten to put in is that this is y equal the square root of that. In order to get it out, I'm going to have, you got it, y squared, and that will give me 1. This is going to be a circle, and it is centered then at the coordinate 1, 0, and the radius is the square root of the constant term, which is here of 1. That gives me a radius of 1. Take a few minutes and copy down what's inside the second radical. Complete the square on your own, then turn the video back on to see if your answer matches mine. Here's what I got for the second semicircle. The formula here is the square root of -72 plus 18x minus x squared, all underneath the radical. I just pulled out the part under the radical, called the radicand, and wrote it in descending order. Notice the -72 is not a part of completing the square. I compute b divided by a to find out what the new expression or coefficient in front of the x term will be, -18. This forces the coefficient of x squared to be +1. This is what I need to complete the square. Then I take half of that number and got -9. This is what will end up inside the binomial that is being squared. Now I need to know what number I have to add and subtract in the parentheses to force that binomial square to occur. I take the half of b over a, which was -9, and I square it. That gives me 81. Adding 0 gives me +81 minus 81. The first three terms in the parentheses become the binomial being squared. The -81 is not part of that, so it gets bounced out and multiplied by the original a. -1 times -81 gives me +81. Notice the -72 is just tagging along for the ride until this point. Then I can combine 81 minus 72 to get 9. This gives me 9 minus the binomial square. Since this is under a radical and equal to y, I can square both sides to get y squared equal the radicand. This then will let me move the binomial square to the left side of the equation, which gives me the equation of a circle with center at 9, 0, and radius the square root of the constant 9, which is 3. Now let's go back and see where we are. I know that this is half of a circle and this is half of a circle. Let's compute the area for those two half circles using the formula for the area of a half circle. The area of a half circle is 1/2 pi r squared. In the first circle, which is much smaller, my radius was 1. That means that I can write the area of the small circle, or the small half circle rather, as 1/2 of pi times 1 squared. That will just give me pi divided by 2. That means that in my formula, the area here is going to start with pi over 2. What about the area under the larger half circle? If I move down, I can use that formula again, and I found that down here, I need to use the formula for the area of the half circle, which again is 1/2 pi r squared. In this case, r is 3, which is going to give me 1/2 of pi times 9. That's 9 pi divided by 2. That would be the area of the larger half circle. What's left to compute? Looking at the picture, both of the half circles or semicircles were above the axis. I need to know about the area below the axis. I was told to find both net signed area and total area. The two above the x-axis will always be positive. Combined, these two together would give me 10 pi over 2, or 5 pi. What about this area below? This is a triangle, so I can use the formula for the area of a triangle. That is 1/2 the base times the height. I need to be able to figure out what coordinate this point right here has. In order to do that, I can either compute it or I can simply use my head. It looks like it's directly under 4. 4 minus 4 would give me 0, the absolute value of which is still 0, and 0 minus 2 would be -2. That point there then must be 4, negative 2. If I use 4, negative 2 as the coordinates of that point, then the height of the triangle is negative 2. The width of the base from 2 to 6 is 4. Let's compute that now and put it into our equation. That means that I would have a negative area because of the negative height. This would be plus 1/2. The base is 4, but the height is negative 2. This will give me net area. The net area here would then have to be, let's use a different color, 5 pi from the sum of pi over 2 plus 9 pi over 2, giving me 10 pi over 2, or 5 pi. Then, to compute this area, I would end up with negative 4. This would be my net area. That's not, however, my total area. If these represented some kind of velocity versus time graph, this would be my displacement from where I started my trip. When I look at total area, on the other hand, the total area is going to take the area above the curve, 5 pi, and add to that the absolute value of the area below the curve, in this case negative 4. That would give me a total area of 5 pi plus 4. This would represent, on a velocity versus time graph, the total distance traveled. We're now ready to talk about properties of the definite integral. Let's talk about some of the properties of the definite integral. These will be used in this section and from now on throughout all of calculus and differential equations and even linear algebra in order to evaluate definite integrals. Some of these are similar to the properties of indefinite integrals. The properties of indefinite integrals do apply to definite integrals as well, but the definite integrals have properties that don't relate to indefinite integrals due to their limits of integration. The first property that you see written here is that the integral from a to a of a function is equal to 0. Let me show you on a graph what that means. Scrolling down, I have a graph down here. Let me produce for you a graph across that picture. If I have a function that looks like this, and it is continuous, the integral from a to a of f of x with respect to x means how much area is underneath the single point at a. When the lower limit of integration matches the upper limit of integration, then the width of that integral is 0. Even though the height has some value, the width does not. And that gives you 0 times the function value at a, which of course is 0. Whenever the lower limit of integration matches the upper limit of integration, you get 0. Let's look at the next property. Property 2 says, if I have the integral from b to a of a function, it's the opposite of the integral from a to b. What does that mean? Let's come back down to our picture and draw something that looks like that. Again, here's a function that I can call f of x. What does it mean then to say that the integral from b to a of f of x dx must be the opposite of the integral from a to b of f of x dx? If you're looking at these, what they're saying is that normally if a is smaller than b, then the area between the curve and under the curve would of course be this area here, shaded now in pink. What happens when you reverse the limits of integration? Instead of having the lower one, the smaller value at the lower limit of integration, what if you put it above? Well, what that means is you subtracted the width of your interval in the wrong order. So of course it's going to be negative. You're still finding the height, but instead of computing the width of the integral as b minus a, you're computing a minus b. Well, of course it's negative. That just means that if you switch the limits of integration, you can put a negative out front. This will let us solve all kinds of problems. For example, suppose you're given an integral that is in the wrong direction, such as 3 to 1 of f of x dx. You know that 3 is not less than 1. You can simply reverse the limits of integration to the proper order by multiplying the definite integral by a negative. That fixes it. Sometimes, later on, after we've learned the fundamental theorem of calculus, if you have too many negatives involved, switching the limits of integration, even if it puts the larger value on the bottom, could be a way to simplify it by eliminating some negatives. This is a really good trick to keep in your back pocket. Let's take a look at property number 3. This says if you have the integral from a to b of two functions added together, it's the same as the integral from a to b of the first function plus the integral from a to b of the second. Rule 4 is the same, but instead of a plus in between, we have a minus. This is similar to the rules that we've seen before for derivatives and limits. The derivative of a sum is the sum of the derivatives, and it turns out the same applies to integrals for definite integrals. The definite integral of a sum is the sum of the separate definite integrals, and the same applies for subtraction. This should make sense to you since in fact definite integrals are limits of Riemann sums. I can't show you exactly what it looks like, but I tried to give you a sense of what's happening by showing you this graph here. This graph is illustrating for you property number 3. In purple here, you see this parabola which represents the function f. The line in blue represents the function g. If I were to add the line and the parabola together, I get a sort of a lopsided looking parabola, which is the one here in orange. The area underneath f would be the area here that is darkest, but also includes this area here between x equal a and x equal b. The area underneath g would be this region here, which looks like a trapezoid. The area under the combined functions would be all of this space here underneath the entire orange part between x equal a and x equal b. If you can imagine in your head then that we are trying to take the purple area, which would be this area now with the dashed purple lines, and we were going to add to that the area in blue now with the dashed blue lines. Let's see if I can get these going in the opposite direction. If you added those two areas together, you would get the entire region that is shaded in the picture under f plus g. It should make sense to you that this is so. What are the next properties? We've talked about properties 3 and 4. Sum and difference of integrals is the difference in sum of two integrals. When we're looking at property 5, it says if you have a constant times a function, the constant can be pulled out. Since this applies to derivatives and limits, this should not be a surprise to you either. The final property is the one that's probably going to be a little bit different for you, but it should make sense to you as well. This says when you do the integration from x equal a to x equal b, you can split it at a value c that's between a and b and compute the integral from a to c and from c to b and add them together. Let me show you a picture of what this would look like. Let's again draw some function f over this area. Now let's take a c value that's going to be between a and b. Let's compute the area under the function between a and b by marking off the different regions. You can see the trapped area there. What they are saying by breaking it apart is that if I wanted to, I could split this area as well at whatever C happens to be. Then I could compute the area on the left side, now shaded in pink, and I could call that area the integral from a to c of f of x dx, and then I could add to that the area on the other side. Let's shade that one in blue. If I shade this region in blue, then can you see that if I add those two areas together, I will in fact come up with the entire area under the function. Oops, I need to change colors again. If I add those together, I'll get the entire area under the function between x equal a and x equal b. In other words, provided the upper limit of this one matches the lower limit of that one, I'm not missing any of the area between x equal a and x equal b. You can do this finitely many times and you will still get precisely the same area. The next few examples use the properties of definite integrals to compute them. We don't yet know how to compute the definite integrals without using geometric formulas for rectangles, circles, and triangles, so they have given us the values up here. They are told that the integral from 0 to 1 of x dx is 1/2. The integral from 0 to 1 of x squared dx is precisely 1/3. And the integral from 0 to 1 of x cubed dx is 1/4. The thing that you need to note about all three of these is they have the same limits of integration. We're talking about the exact same interval in all three cases. Now let's take a look at the first problem. In order to do this, since these are all added together, I can split the definite integral of a sum into the sum of the definite integrals. This gives me the integral from 0 to 1 of 1 dx plus the integral from 0 to 1 of x dx plus the integral from 0 to 1 of x squared dx plus the integral from 0 to 1 of x cubed dx. Now the last three I have expressions for up here in the directions. I know what the last three are going to be. They're going to be, for x dx, I replace with 1/2. For x squared, I replace with 1/3, and x cubed gets replaced with 1/4. However, how do we deal with this one? Well, let's draw the graph and see. Since the integrand in this definite integral is 1, that corresponds to the graph y equal 1. Let's come down here and graph the graph y equal 1 on this particular graph. To make it easier, I'm going to let this value here represent 1 on the x-axis and this value here represent 1 on the y-axis. The graph of y equal 1 then would be the horizontal line at y equal 1. Now let's take a look again at the definite integral. The limits of integration extend from 0 to 1. That means I need to know about the vertical lines extending from x equals 0 and x equal 1. X equals 0 is the y-axis. X equal 1 is the vertical line here. Remember that all are given with respect to the x-axis for the area. That means that the region I'm looking for is the one closed off in here. Since this is an area that is 1 by 1, I can compute that pretty easily. The area there must be 1 square unit. Now I can add that in to my equation. This gives me 1 plus 1/2 plus 1/3 plus 1/4. I will need a common denominator, but I believe that would be 12. In that case, then, I can write this as 12 over 12 plus 6 over 12 plus 4 over 12 plus 3 over 12. Adding numerators only, I get 25 twelfths. That tells me the answer for this particular problem is 25 twelfths. Let's take a look at the next problem. In the next problem, I have the definite integral, again from 0 to 1, of the integrand 1 minus x plus x squared minus x cubed. Now I can split it up, since these are sums and differences, and write it in the following format. The integral from 0 to 1 of 1 dx minus the integral from 0 to 1 of x dx plus the integral from 0 to 1 of x squared dx minus the integral from 0 to 1 of x cubed dx. Recall again that our values are given here in the directions. Note that I have also now found that the integral of 1 dx is 1 square unit. Then I can write the following. This must be 1. The integral of x dx was 1/2. The integral of x squared dx was 1/3. And the integral of x cubed dx was 1/4. Note the changed signs. Writing in common denominators, this gives me 12 over 12 minus 6 over 12 plus 4 over 12 minus 3 over 12. By adding and subtracting the numerators only, I get 12 minus 6, which is 6, plus 4 is 10, minus 3, which is 7. My final answer then is 7/12. Let's take a look now at our next example. In example 7, I have the same setup, but this time my integrand is a binomial factor being squared. In order to compute this, I will need to multiply out the binomial squared, since I don't yet have any techniques to allow me to integrate it without it. In other words, first I have to do some work to the integrand to get it into a sum or a difference, so I can split it up. I have no rules for products or powers at this point. 1 minus x times 1 minus x would give me x squared minus 2x plus 1 for the integrand. Then I can split this up into 3 different integrals. The integral from 0 to 1 of x squared dx, and then I have plus the integral from 0 to 1 of negative 2x dx, plus the integral from 0 to 1 of 1 dx. I know the integral from 0 to 1 of 1 dx gives me a square unit. This will give me a plus 1. I also know from the directions that the integral of x squared dx from 0 to 1 is 1/3. This leaves the middle integral to deal with. Notice that the negative 2 is a constant, so I can bring it to the outside. That will let me write minus 2 times the integral from 0 to 1 of x dx. Now I can use the value given in the directions, that integral is equal to 1/2, to complete the problem. This then gives me 1/3 minus 2 times 1/2 plus 1. This gives me 1/3 minus 1 plus 1, or 1/3 for the final solution. Let's take a look at another example. In the next example, I have to do a similar thing. In this case, you'll see that I have a 7 here and a 5 being multiplied by the x cubed. Because this is a difference, I can split it first into the difference of 2 definite integrals, from 1 to 7 of 7 dx minus the integral from 0 to 1 of 5x cubed dx. Now I can think of the 7 as, in fact, 7 times 1. That will let me write 7 times the integral from 0 to 1 of 1 dx. Then, for the next part, I can take the 5, that is a coefficient, on the x cubed, and I can pull it outside the definite integral. That will give me minus 5 times the integral from 0 to 1 of x cubed dx. Now I can use the known value that I found in the first example in this section of 1 to give me 7 square units for the first part. I can use the known value of 1/4 for the integral of x cubed dx over 0 to 1 to give me -5 times 1/4. This gives me 7 minus 5 over 4. The common denominator is 4, giving me 28/4 minus 5/4, which would give me a final answer of 23/4. Let's move on to the next. We have one more small theorem that we want to discuss before we close this video. This is called a comparison theorem. We won't be using this a great deal, but it is something to keep in the back of your head. The part 1 says, suppose that you have a function which is greater than or equal to 0 for all the values over a closed interval. In other words, it may touch the x-axis, but it doesn't go below. Then the area over that closed interval must also be greater than or equal to 0. If you draw a picture, this should make sense to you. Let's suppose that the function does touch but stays above. In this case, what we would need to find then is the area between the curve and the x-axis and underneath it. This area would in fact always be either positive or 0 on the part where it barely touches the axis. That means that the area itself is going to be greater than or equal to 0. Let's look at the next part. This says, what if I have two functions and f is greater than g? It does not say, however, that f and g are above or below the axis, but that the y value for f is always above the y value for g. And this is true for a less than x less than b. Then the area under the f function has to be greater than or equal to the area under the g function. Again, this should make some sense to you. If I were to draw a picture of what this looks like, suppose I drew a function f in purple and another function g in orange. Note that f is always above g. If I were then to look at the regions under these two curves, notice that the area under the curves and above the x-axis is going to have to be less under g than there would be under f. That's simply a consequence of the y value always being greater than the y value on g. The last one is a little bit different and something we'll use to develop the average value in the next video. This says, suppose you have two constants, lowercase letter m and uppercase letter m, and that the function is always between those two. Then the area over the closed interval from a to b has to be between lowercase letter m times the width of the interval and uppercase letter m and the width of the interval. Let's draw a picture that demonstrates this particular idea. In this case, I will again draw the function f in purple. Here's my interval between a and b, represented with the vertical lines now in red. The x-axis is, of course, going to be also in red. Now let me draw two lines representing uppercase letter m and lowercase letter m. For uppercase letter m, I'll use a green line. Let's look at this one now. Let's suppose that m is here. If I were to draw this, this would be the line representing y equals m. Let's find now a lowercase letter m where the value is below the function value. In this case, when I'm doing that, I need to pick something that over the interval is always below the y value for the function. This, of course, is y equal to lowercase letter m. If I were to look at these two regions now, let's extend the vertical lines to go above uppercase letter m. What does it mean then for the area under the curve of f to be between those two? Let me represent that area now. the area between a and b and under f of x dx, let's represent that with the pink. That would be this area right here, shaded now in pink. What does it mean then to take lowercase letter m and multiply by b minus a? Well, b minus a is the width here, and m would be the height of a box. Let's represent that with the yellow. It's not going to show up as well because I've got a color over a color, but we'll do the best we can. That box there is definitely less area than is under the function f. What about m? Let's represent m's with green. I'll try to use a contrasting green, maybe lime green. This area here, which includes the area under the function and the area under lowercase letter m, is definitely more area than what was under the function. That's all it's saying, that the area under function has to be greater than the rectangle at height m and less than the rectangle at height uppercase M. That's all that one implies. This is the end of this video. There's one more video for section 5.2 where we will discuss the average value of a function.